In this video, we'll be looking at summations. So, summations are just a method of adding things up. For example, 1 plus 2 plus 3 equals 6, and this can be written in with sigma notation. So, sigma is a Greek letter, I think it's the Greek letter S, and it's used with the letter R, and that is the rth place. So for example, with our sequence just there, it can be with our sequence just there, the lower limit, 1, our starting point, is at the bottom, and our ending point, that's meant to be n equals 3, I apologise, is the last number that we add. So it's just the rth place, so when r equals 1 it's 1, and then this is plussed onto when r equals 2, which is 2, and so on, which equals 6. Okay, so adding large numbers can be an annoying task to do, because you don't want to add up to like 50, for example. So let's try and formalize this and see what we get. So let's say that n is the end point and r equals 1, the start point. We can say that this is just 1 plus 2 plus n minus 1 plus n. Alright, and we can actually multiply this by 2, and this you'll see why in a sec. So for this, it's just 1 plus 2 plus n minus 1 plus, there should be a dot dot dot, plus n, plus this again, okay, but you can join all of these together, so this n goes to that one, and this 1 can go to that n, and the 2 can go to n minus 1, so therefore 2 times this just equals n plus 1 plus n plus 1 all the way up to n, well, the nth place. This means that there's just n lots of n plus 1, meaning that 2 sigma of r, oh, apologies, 2 sigma of r equals n times n plus 1, and so sigma r equals a half n times by n plus 1. Two more types of sequences I'd like to show is the sum of squares. So we're using our sigma notation again. It's actually r squared, so it's r, so this is 1 squared plus 2 squared, and so on. Now the proof of this is a bit too long to show, but it's quite interesting if you'd like to go search it for yourself. So this can be generalized to be 1/6 times by n times by n plus 1 times by 2n plus 1. Okay, where n is the final point. And well, there is r cubed as well. Now I'd just like to show you r for 3, which equals 6. 1 plus 2 plus 3 equals 6. And then for r cubed, for the same thing, 1 cubed plus 2 cubed plus 3 cubed, that equals 36, which equals 6 squared. And if you do this for 4 and 5 and 6 and so on, you find the same thing. It's the square of this. So as I just said, the sum of r cubed is equal to the sum of natural numbers squared. So that can be known as 1/2 of n plus 1 squared which is 1/4 n squared n plus 1 squared. I'd also like to show that sigma of r, or anything actually for that matter, can actually be shown as something else, and I'd like to show that. So let's do it. So it's a plus a times 1 plus 2a plus 3a. Okay, and so that's just a times by 1 plus 2 plus 3. So therefore that is also equal to that, where a is out. You can take a outside of the summation, basically. Also, I'd like to show that of any term, this, so sigma of x actually, of any term, so for example x would actually be a constant in this case, not a variable as it usually is. This can actually be nx, so let's just see the theory of that. Imagine x is a constant, so that just equals the first x times plus the second x plus the third x plus the fourth x and so on, and actually that is just x plus x n times, which equals nx. Finally, in this video, I'd like to be able to show you how to use summations. Okay, so let's just take this. So 3r squared plus 4r plus 1. So we can use the things that's meant to be an r, by the way. Also, you don't have to say r equals the bottom at here, because it's kind of already assumed that, you know, r equals at the bottom. Okay, so let's do this. That's equivalent to 3 times by r squared plus, and then this one is 4 on the outside, and then there's just 1. Okay, so that equals 3 times a sixth times by 5 times by 6, using the formulae that we were shown, or that I showed before, plus 4 times by a half times by 5 times 6 plus 5 times 1. Alright, so a sixth, so that's 5 times 11, which is 55, times by 3, that is 165, plus 60 plus 5, that equals 230. So as you can see here, you can evaluate these expressions using summation formulae, and it's very useful.